Hello everyone, my name is Horace, and in this video we're going to be going through LeetCode number 300, longest increasing subsequence. So for this problem, we're given an integer array nums, and we have to return the length of the longest strictly increasing subsequence. So as always, let's go through an example to understand the problem more clearly. So given this integer array nums, what is the longest strictly increasing subsequence that we can find? Well, first let's try to find an increasing subsequence, and an increasing subsequence is just finding elements in the integer array such that when we iterate through the array, the elements are increasing and we don't change the order of them. So let's begin with the first element. We can write down 0. Then the second element is greater than the last element that we recorded, so we can add that as well. Now we get a 0 again, and 0 is less than 1. So we don't add that to the current longest increasing subsequence. Then we can take a look at 3, and 3 is a part of this sequence as well, so we can add that. But now we have the element 2, and 2 is less than 3, so we can't actually add this. But if we look at the last element, we can see that there is a increasing subsequence that is actually the longest, so we can have 0, 1, 2, and 3. So this is an example of what an increasing subsequence would look like. And as you can see, we did not change the order of any of the elements. We simply just mapped it to the order that they appeared. Okay, well, now that we have an understanding of what an increasing subsequence looks like in relation to this problem, we can try to develop an algorithm that will help us find the increasing subsequence and more generally the longest increasing subsequence. So we can start off with a similar strategy. We can begin by looking at the first element. Now the first element is 0, so thus far this is the longest increasing subsequence that we've found. Then we take a look at the second element, and it's 1. Well, we can just expand this previous increasing subsequence that we found, and we can make this to be 0, 1. And this is the longest increasing subsequence we found so far. Then we find an element that is less than the last element in the increasing subsequence that we found. But since we've already found it, we know that it will eventually be a part of this subsequence. So we don't have to worry about it for this case, since it's a number that we've already seen. Then we take a look at 3, and 3 is greater than 1, so we should add this to the increasing subsequence that we found. But now we encounter a 2, and this is less than 3, but we have to make sure that any future additions to the sequence containing 2 don't become the longest. So we have to actually add any previous elements that we've seen that would help to make it the longest increasing subsequence. And then we take a look at 3, and we can't add it to the first subsequence, so we have to add it to the second subsequence, and by adding it to the second subsequence, this becomes the longest increasing subsequence that we found. Now, this is a valid approach to solving this problem, but we would have to maintain several arrays to keep track of the possibilities that we might encounter. So is there a way that we can actually just use one array and update that depending on the elements that we see? Well, for this case, we can actually use binary search and just optimize the elements that we pick by rewriting them. So let's take a look at the example again. We start off with 0, and then we add 1. But then we encounter another 0. And every time we encounter an element that is less than the previous element that we've stored in the longest increasing subsequence, we want to perform binary search and update the smallest element that's greater than or equal to this number. And the reason we want to do that is to maintain the integrity of the subsequence and keep the invariance so that it remains an increasing subsequence. But once we perform binary search on this array, we'll actually not be removing anything since this is already an increasing subsequence, and we don't need to worry about this case. But let's move on to the next element. We'll say 3, and we add this because it's greater than 1. Then we take a look at 2, and 2 is less than 3, so we have to perform binary search here. And when we perform binary search, we want to find the element or the smallest element that's greater than or equal to 2. And in this case, the element is 3, so we can just remove the 3 and replace it with the 2. And this maintains the increasing subsequence since we're only dealing with unique values. So we can have a 2 here, and then we look at the final value, which is a 3, and we can just simply append this to the end of the increasing subsequence. And we can see that this array has a length of 4, and this is exactly the answer that we return for this integer array nums. So to determine the time complexity for this algorithm, we have to first take into account the iteration of the original nums array, and that we can do in big O of n time. Also, suppose the worst case is when we have to perform binary search on each of the elements. Then we perform a binary search n times, and the worst case for a binary search is big O of log n. So altogether we have a total worst case time complexity of big O of n log n. And the space complexity in this particular implementation is going to be big O of n, since we're keeping one of the arrays that we'll be returning. However, if we just update the original nums array, which is possible, then we can achieve a worst case space complexity of big O of 1. So hopefully this approach is clear, and we can go ahead and implement it on LeetCode. Okay, we're on LeetCode, and we can start writing the algorithm to find the longest increasing subsequence for some integer array. We can begin by initializing some results array that we'll be returning, and we know that we can store the first element in the array, and this is simply because that we know that it will either get overridden or it will be a part of the longest increasing subsequence. Then we can go ahead and loop through the remaining elements in the integer array, and we can check to see if the current number is greater than the last number that we've seen in result or stored in result. So we'll just check if the number is greater than the last element in result, so result and -1 to get the last element. Then we want to append the current number, so we'll just append it to the array. Then if this condition is false, we want to perform a binary search. So we can initialize our left and right values accordingly. And then we can perform the binary search by using a while loop, and we'll declare the mid, which is going to be the left plus the right minus the left, and we want to divide this by 2. Then we want to check if the middle number is less than the num value that we're looking at. So if the mid number in the result array is less than the num, then we want to increment the left pointer to be the mid plus 1. Otherwise, we just want the right pointer to be the mid. Finally, once we exit this loop, we know that we've found the smallest element that's greater than the number. So we can say result of left is equal to num. And after this for loop terminates, we'll have an array with the longest increasing subsequence, so we can just return the length of the result. And hopefully this should be the solution. We can go ahead and submit it, and you can see that the code is accepted. And this is the optimal solution running in big O of n log n time with a space complexity of big O of n. You can optimize the space complexity to be big O of 1 if you just mutate the nums array. With that being said, hopefully this video helped you and you learned something, and I'll see you soon.